So in class today, we talked about the concept of an isotope, and I'd like to distinguish this from an ion. When we think about the term ion, we're focusing on ions being gained and lost. And then the concept of an isotope really has to do with this fact. So the same element can exist in nature with differing numbers of neutrons. And it's not so much that these neutrons are being gained and lost as much as they're just there. So a good example of this is that sometimes carbon has a mass number of 12, and we think about it, carbon always has 6 protons, always. That would be the definition of carbon. So in this case, it has 6 neutrons, so 6 plus 6 is 12. And then other times in nature, on Earth, carbon can have 8 neutrons, and then 6 and 8 is 14. So we can have these two different isotopes of carbon. And then one common way we represent this is by drawing this right here, which is an isotope symbol, where we list the mass number on top and we list the atomic number on the bottom. Okay, let's apply this to some practice problems. I had a repeat here, so I went and changed this to 20 neutrons also. So first, please draw 3 isotope symbols for atoms with 17 protons and 18 neutrons. So let's look at our periodic table. So chlorine is the atom that has 17 protons. So I'm going to go ahead and write chlorine. And I'm going to go ahead and write the atomic number for chlorine, or the number of proteins on the bottom here, the bottom left. And then to put the mass number up top, 17 plus 18, so we get a mass number of 35. So next, the isotope symbol for the atom with 17 protons and 19 neutrons. So 17 plus 19, so we get 36 up here. And then lastly, 17 protons and 20 neutrons. Still dealing with chlorine because it's got 17 protons, so we get 37 up top. So it looks like these are 3 different isotopes of the chlorine atom that can exist in nature. Okay, question 2. Which isotope of carbon is probably the most abundant in nature? Now, we might not know for sure, but I think if we look at our periodic table and look at carbon again, and you see that carbon is 12.011. So this is an average, the average mass of all the carbon isotopes on Earth. And I think all we want to do is look at what whole number this is closest to. And 12.011 is definitely closest to 12. So I would probably say carbon 12 is the most abundant isotope of carbon on Earth. Okay, question 3. Please calculate now the average atomic mass for boron using the following data. Now, one thing I think we want to not do is look at the periodic table and just use that answer. I think we always want to use the data we're given, because it might not always match. And that data is probably the best data that you see on the periodic table, but let's use this data. Now, if you want to calculate the average atomic mass, what you're going to do is you're going to take the mass number of each isotope, and you're going to multiply it by the percentage, but get rid of the percentage and turn it into the decimal. So we're going to do 11 times 0.801, and then we're going to add that to the other isotope of boron, boron 10. So 10 times 0.199. So we're going to calculate this, and when you multiply 11 by 0.801, you get 8.811. When you multiply 10 by 0.199, you get 1.99. And we add those two values, and we get about 10.80. And we're just going to go to the hundredths place here. I don't want us to think about sig figs for now. Okay, let's keep going so we got some time. Please draw 2 isotope symbols for atoms with 5 protons and 5 neutrons. So which element has 5 protons? We got to look at our periodic table here, and we see that boron has 5 protons. So we get 5 below here. So 5 protons and 5 neutrons would mean we have boron 10, and then 5 protons and 6 neutrons. We still have boron because it's got those 5 protons, and then 5 plus 6. So we get our mass number of 11 on top here. Okay, last problem. This one's kind of lengthy again, but if we can do this one, we should be able to do anything. Please calculate the average atomic mass for iron using the following data. So again, we're going to look at each of these mass numbers and multiply these by the percentages we're given. So we would do 54 times 0.0585 We're going to add that to 56 times 0.9175. We're going to add that to 57 times 0.0212. And we're going to add that to 58 times 0.0028. Now, when we multiply 54 times 0.0585, we should get 3.159. When we multiply 56 by 0.9175, we should get 51.38. When we multiply 57 by 0.0212, we should get 1.20 or 1.21. And when we multiply 58 by 0.0028, we get 0.16-ish. And when we add these all together, we should get about 55.91. And now I think if you look at the periodic table, you see that iron, using the best data is maybe 55.85-ish. And this is a good example of how you should use the data you're given and not just jump to the periodic table. Okay, so I hope this helped with understanding isotopes. If you need any more practice, come see me.